TV sets are on. Everything's cool. Let's have a take-home test. Thursday. I'll post it on the web. Give you a week to do it. Okay? It'll be fun. It'll be educational. Be something you'll be able to tell your grandchildren about. No, not really. Won't be that bad. Okay? I kept making up homework problems, but they all sounded like great take-home test problems instead. So I made the homework into a take-home test. So I will be posting that. I might post it early. There's really no reason to wait to Thursday. So you might check in and see if it is posted. But I will be posting it by Thursday. But I won't post it before tomorrow, since some of the ed students don't see this tomorrow. And there's no way that we can give you a running head start. We will end the exam during this period on Thursday, a week from Thursday, whatever that is. Okay? Huh? During the period.
What do you mean by that? I'm serious. Like, do we hand in the exam?
Yes, hand in the exam.
Sit here and write more answers because it makes a difference.
Oh, okay. Actually, that's a good point. We'll do it at the beginning of the period. I would do it at the beginning of the period. Okay. Thank you. Okay. Very good. Okay. Last time we were looking at error backpropagation. We just finished the derivation. Beautiful piece of math, as I think you can see. Let's review what we're doing with neural smithing. If we could look at the overhead. Thank you. Okay, so here's backpropagation. We looked at the general feed-forward architecture. This was the one that was proposed in the book, where the nodes, a node, by the way, is either an input or a neuron. The nodes are numbered sequentially. And then we looked at the node activation and output. And then using steepest descent, we desired to generate the partial of the error with respect to each of the weights. We did that, and we found out really interestingly that in order to have backpropagation, that we trained the neural network using a very simple updating rule, which we will review very quickly. And this is, again, the weight update rule. The entire concept of backpropagation is that one is presented with the training data, one goes forward in the neural networks, paints all of the nodes in accordance to whatever the state of the node is, looks at the output, looks at the error of the output, and begins to work back towards the input, painting all the nodes with the deltas. Then the incredible thing is that the steepest descent algorithm, which we generate, requires, if we want to update a weight between two neurons, we only need the state on one side and the delta on the other side in order to update the weights of the neurons. So therefore, we do not need any dells or states of the neurons far removed in order to update a weight. I think you can see this is kind of biologically interesting, because hopefully that's the way we would like to do things biologically. We would like to be able to do things such as in the McCullough-Pitts way of updating neurons, where only the neurons, the states of the neurons, determined the degree to which the neuron was updated. Now, this has biological significance. One of the questions that we might ask is, does it have engineering significance? And the answer is probably no, not really. We're really not interested in weights being updated by neurons. It's nice and aesthetic, but really what we're interested in is getting a neural network or one of these regression machines to actually work. And if it updates globally instead of locally, that's okay. We don't care, as long as the final result works well, okay? But I think you can see that the people in biology were kind of excited about the concept of error backpropagation as it flushed out in the layered perceptron. Now, once we do this, there's a couple of ways to, actually there's different ways to do this, and this to apply backpropagation, and there's batch versus the online learning, which is the next thing we'll talk about. We have the weight update rule. If you remember the weight update rule, it's an incredibly simple rule. I think we put it on the board last time. I'm not going to put it on the board again. because you can just simply refer to your book or the notes. There is, of course, the question of step size, as we always do in search sort of techniques, especially steepest descent. We have a variation or a trade-off between the step size, overshoot and undershoot, just like with the control system. Now, there are different ways of performing the operations, and we're going to look at three of them. One is sequential online training, shuffled online training, and continuous input online and batch training. These are all three different ways of applying backpropagation, and let me review them. Sequential online training means that you have a fixed set of data, and this fixed set of data is being repeatedly presented to the neural network in a cyclic sort of fashion. The idea being is that the neural network, as it's given the first piece of data, adjusts itself to better recognize that first piece of data, but then when we get to the end of the list, it probably forgot what the first adjustment was, so you got to go back and you got to tweak it again. And you have to keep on doing it until there is a convergence. Now, there's a problem associated with doing that in that the neural network might be affected by the actual ordering of the data. If you can think of the data being ordered in a certain fashion and you repeatedly present this ordered data to the neural network, that might in some way affect the final training of the neural network. So one of the things which is done, interestingly, is shuffled online training, wherein one takes data and you present one epoch, then you shuffle the data and present the epoch again. Shuffling the data removes the sequential presentation of the data the same old way. Anybody know how you shuffle? This is, I think, a standard question they would ask you if you went to work for Microsoft. How would you shuffle data? You have a list of data, and what you'd like to do is you would like to rearrange it in a random order. Anybody know? Oh, but we talked about it, didn't we? Yeah, so that doesn't count. Okay. Anybody else know? Best way to shuffle, an easy way to shuffle the data, I don't know if it's the best way, but certainly the fewest lines of code in a MATLAB sort of scenario, is to take the data and with each piece of data associate with a random number. Okay? So use the random number generator to generate parallel vectors of the original data and a random number vector, and then use a simple statement in order to take that random vector and to rearrange it from smallest to biggest, and you carry the other numbers with it, and then whatever those numbers are, that's the shuffled piece of data. And if you use a different random number vector every time, you're going to get different shuffles of your data. So certainly that's a very simple way to perform the shuffling of the data. So shuffling of the data keeps us away from any sort of structure which might come about from the sequential presentation of the data. And then there is batch training. Batch training, as you might expect, this was actually the derivation that we gave on the board. Batch training accumulates all of the errors, and all of the errors are accumulated at once before an update on the weights is done. This is another way of doing it. Then there's continuous input online training. What do I mean by this? There might be instances, for example, where one is training a neural network in order to distinguish a signal in the presence of noise, and maybe the noise is being generated in real time, or the noise is being generated by a random number generator or such, but in either case, there's really no need to repeat the data because the noise is different all the time. If you're monitoring, for example, a telephone line and you're using a modem and you're trying to have a neural network equalize your line, then the neural network is going to have to adapt real time to the continuous onflow of the input signal, which is going to have noise which repetitively is changing. So you're not going to be presenting the same data over and over and over and over again. So this would be an example of the continuous online training and batch training. The results are conceptually different, and I'll give you the situation that we have. This is from the book. First of all, for online training gives the, if we could focus in here, please. Yeah, more. Good. Okay, here we have the situation. This is on page 60 of your text, which illustrates the sort of randomness that one gets into when one uses online training. The problem is that every time that you present a new piece of data and you update for that single piece of data, you have an error surface that you're trying to adapt to, but that error surface changes for every presentation of the data, right? So what happens is you might present the first data and you'll step in this direction. If you presented the second piece of data, you'll have stepped in this direction, the third piece of data in this direction, etc. So each of the different pieces of data, if you're at the same place, it depends on the next value of the data that you present, is where you would perform the step at. You remember the error is the difference between your output and your target function. If you present one piece of data, well, you have an error which is dictated by the output for that. If you present another piece of data, say input 2, you're going to have an output 2 and a target 2. It's going to be a totally different surface area that you're optimizing for. So hopefully, all of these different steps will in some way compromise with each other to give you a true gradient which is conducive more of the batch training way of doing things. It is even possible to get step sizes, as it shows here, which are totally counter to the way that you want to perform your operation. Now, on the next page, we actually have online training, and this is online training, and this looks at the actual training of the neuron, or of the neural network for a shuffled version of the data. And for the shuffled version of the data, here we present the first value. Well, the first value went over here. We presented the second value, went over here, third value over here, fourth value. So it begins just to oscillate wildly because each piece of the data is under the influence of a different error surface, and so you're going to get this random sort of way of doing things. But hopefully that all of these things will kind of average out, and eventually you'll slop around to the minimum. And it works pretty good, or pretty well, I should say. By the way, this is the case when we shuffle the data. Each of the circles corresponds to an epoch, I believe. Because we actually have a number of different patterns here associated with the steepest descent. And you can see that once we get around here, we kind of slop around the result and hopefully converge to it. But this is with the shuffling, and you can see that the shuffling actually presents a stochastic element to the search. And if we were to do this same exact search again using this as the initializing point, and we shuffled, we would be using different random number generators, and we would be actually, as we did the shuffles, we would generate a different cattywampus approach to the origin with the shuffling, correct? Now, if we didn't do the shuffling, we get on page 61 more of a case like we have here. This is on the bottom of page 61. This is the case of the online training where there is no shuffling. Well, if there is no shuffling, then there is a structure which is imposed on the training process by the data itself. And you can see exactly what happens. Each one of these little humps corresponds to all of the training with the epoch. And since the first training data always kind of pushes it up and the second one kind of pushes it down, we always get this same sort of shape when we go through the data one point at a time. So we get a structured sort of convergence to the result. Does that make sense? Since we're presenting the data in the same sequence every time, we obtain this sort of result. And then the nice thing is if we use batch training, which is favored in many cases, not always, but in many cases, we get a nice smooth convergence. If we could go down a little bit here, please. A little more? Okay, that's good. We have a situation here where this is the batch training. And the batch training, you can see, is doing the kind of a steepest descent sort of operation in the sense that it remains orthogonal. These are the contours of the error surface. This is only a two-dimensional error surface, of course. And the batch training is keeping pretty orthogonal to it and zooms in on the result. So this hopefully should give us an idea of the different mechanisms of convergence for the three types of training that we've talked about, which is online training with shuffling, and then the batch training approach. One of the problems with neural networks, which you will see many references to, is the enormous amount of training time that it takes to train a neural network. Even with gigahertz sort of machines, it can take, for moderate-sized problems, days for the neural network to train, because you are dealing in such a high-dimensional space, and many times in relationship to that space, your step size is so small that you can take a heck of a lot of time in order to converge. Now we're going to talk a little bit about learning rate and the different concepts of learning rate. We've talked a little bit about a learning rate. The learning rate that we have talked about thus far has been a learning rate that has been fixed. In other words, every neuron has the same value of eta. Remember, eta was the step size? There are also some different processes, and we'll talk about them briefly, wherein these step sizes are assigned to different neurons. Each neuron has a different step size, and it is determined adaptively as the neural network trains. But one of the things that you will find in training is that there is something which really, really helps you in life, and that is the concept of applying momentum to your process. Momentum gives inertia to the search, which means the following, that the step size change has a memory, and that if you take a step size in one direction, that your next direction cannot totally undo it. You can't turn around and go back where you came from. You have to keep going downhill. The analogy is that you're going downhill with the steepest descent. Remember, you're blind and you're on the farm in West Virginia and you're looking for the lowest spot. Well, you take a step, but you also keep a momentum going so that your next step has to be in some sense in the same direction, or have a component in the same direction as your previous step. Does that make sense? So you develop a momentum or a memory associated with your step size. Now, the simple way of performing the momentum is as follows. Remember, before, the change in the weight size was equal to minus eta times the partial of E with respect to the weight. This was the error backpropagation result. So this is the step size. With momentum, it's exactly the same thing. That is, we have a step size, plus we want to make sure that we step kind of in the same direction as we stepped in the previous step. And in order to do this, we're going to add on another parameter. And let's see, I should put T here. T is the iteration number. Okay, so the step that we take at time is equal to t is steepest descent. Yes, we still want to go downhill, but we also want to step in the proportional to, and this is a coefficient which we'll talk about in a second. We also want to go in a direction which is similar to the step that we previously took. This will keep us from doing crazy things like going 90 degrees and turning around and going back from where we came from, because we have a momentum. Now, clearly, we have two values now. We have the step size, by the way, which is also referred to sometimes as the learning rate. And we also have a parameter here which is referred to as the momentum coefficient. And these are values which one chooses in determining the search. Clearly, momentum has its problems too. Suppose you have too big of a momentum, what's going to happen? If your minimum is here and you have a step size here and you have too much momentum, you're going to totally pass it, right? Just like in a car, which you're going too fast, you can't make the curve very well. If you have lots of momentum, you can't go around curves very much. So if you have too much momentum, you're not going to go around the curve very quickly. If you don't have any momentum, it turns around, you can jerk around a little bit too much. And if you jerk around a little bit too much, it can keep you from getting where you want to go also. Now, there are some figures, which I'll now share with you. These are on page 88 of your text, which show the difference between having momentum and not having momentum. This is on page 88. If we could frame this, please. Here we have a situation where we have a without momentum, and this is for a small step size and a large step size. As you can see, I lost my pointer. There it is. Okay, great pointer. Here we have a very small step size, so the very small step size is going as we would expect. If we have too large of a step size without momentum, we have this sort of scenario, which is referred to as cross-stitching. We are cross-stitching back and forth between things. And there is no momentum. There's no momentum, so we can go back in the direction that we came. We can turn 90 degrees. There is no sense of a momentum of running downhill, which is a nice way to think about it. Now, if we take the same exact problem and we apply momentum with us, for the small step size, we don't see a lot, because if you're taking small step size, momentum doesn't add into things very much. It does turn out the small step size actually goes over a little more. The small step size without momentum actually goes with a trajectory which looks more like this. And here's the large step size. If you recall before, without the momentum, we had the cross-stitching. Now with the momentum, even though apparently we can come back here since going downhill is so great here, yet we don't have this ability to do this incredible increase in cross-stitching, and we do converge much better. In fact, in all air back-propagation that you use, you will need to use momentum, because many cases the thing just doesn't converge without momentum. You get this cross-stitching action, which just kills you. There's always a question of what value do you use for a step size, what value do you use for the momentum. A rule of thumb, if you just want a generic answer, is a step size of 0.1 is something that you can start with, and momentum of 0.2. Again, these are rules of thumb. The convergence is going to be very dependent upon your data set that you're training with, but this is always a good place to start. So this is learning rate and momentum. So there are a number of ways to deal with this. Momentum is probably the most commonly used. There are some other techniques which are called weight decay, and all of these can be used in conjunction with each other. There's no reason that one couldn't use both weight decay and momentum at the same time. Let me explain to you what we mean by weight decay. It has the flavor of momentum. So this is momentum. And now we're going to have weight decay. For weight decay, we take the basic same error propagation rule, del W of t, and we replace it by the standard steepest descent relationship. And then we actually subtract off it a percentage of the previous weight. Now notice this is not the delta, this is the previous weight. This has a very nice property associated with it. And the property is as follows. We have two contrasting things happening here. We have this, rho by the way is always chosen to be less than 1. So it always has the effect of forcing this delta W down. In fact, if you're on if this term doesn't appear and we have just this relationship, the solution to this difference equation is simply something which decays exponentially to 0. It's a first order differential equation. Yes?
Should that be 2 minus 1? Or is it
I'm sorry?
for rho WT, you said the previous weight? The rho WT minus 1?
Oh, yes, it should be. Thank you. see if that's in the book. That's not in the book, but I'm sure that makes a lot of sense. If this is not here, this will eventually decay to zero. Now, one of the nice things about the weight decay is its ability to perform generalization. Many times you wonder whether you should put too many neurons in or not enough neurons. Remember we talked about the effect of underfitting and overfitting of data points and the way you ascertain that through the use of cross-validation. Well, the nice thing about weight decay is that if you have overdetermined a system and there are some weights that you don't need, this will have the effect of driving certain of the weights that you don't need for the undetermined system to zero. Because what happens in the dynamics is this term eventually becomes very small, and these delta weights become such that we simply have this term, and the weights begin to decay to zero and becoming non-participatory in the neural network. We are going to show you, in fact, Ben has said that we will be able to, he'll be able to give us a presentation of some of the in-house neural network software that we have probably this coming Thursday, so that will be nice.
In the book, you have that weight decay equation without the -1.
Yes, I do. It actually doesn't matter because if you think about it, yeah, if you think about it, it really doesn't matter because in the book it does have this W of t. And your first reaction at looking at this might be, well, there's no t-1. Where's the memory associated with this? Until you realize that the new weight of t, say, +1 is equal to the old weight at t plus the delta weight at t. So it can be either one. It doesn't matter. Okay. You'll get incrementally different performance with the two. The next thing I'd like to talk about is the error surface. Notice we're just buzzing through the chapters here. The interesting aspect is I'm hitting the highlights of these things. In the book, there's a lot of things that I am skipping. I'm skipping, for example, Chapter 7 on weight initialization techniques. And I'm hitting some of the remarks that I consider to be most important. One of the interesting things about neural networks is that they do take a long time to train, and the reason they take a long time to train is because of the error surface. Number one, the error surfaces typically exist in very, very high dimensions, and number two, we have to do things in order to assure that we don't drop into local minima. We would like to have a global, very nice minima. In watching the dynamics of neural networks train, it's very interesting to watch because many times if you look at the convergence, there will be nothing happening and then there will be a change as the neural network begins to train. And we'll see the manifestation of this by looking at some of the errors and the error surfaces which are typical in neural network trainings. Okay, the error surface. Point number one, due to saturation, error surface and weight space can be conical. We make the following recognition here. Suppose that we have a sigmoid and we have a weight, and this weight is such that it gives us an activation which is here, which gives us a state of the neural network equal to 0.999. In other words, this is the activation, the summation of the other states times the weights from the states. And this is the activation for this particular neural network. So we have these weights here, which are driving the states of the other neural network, and this gives us the activation. So the activation for this neuron, according to the output of that sigmoid, is 0.9. Now, what happens if you take each of these weights and you increase each of those weights by a factor of 50? What's going to happen is that instead of being here, you're going to be at 50 times A, right? Because, by the way, A is equal to A. I am physically unable to be consistent, so we'll just keep this in mind. If you multiply all of the weights by 50, in other words, replace each of the weights by 50 WK, then we're going to end up here at 50 times A. Do you agree with that? If we do that, what's the state of the neuron then? Well, instead of 0.9, it's going to be 0.999. It hasn't changed very much. We say that the neuron is saturated at this point. It is saturated because it has gotten to a point where it becomes relatively insensitive to the weights. Does that make sense? If we have a weight saturation, this means that if all the weights get big enough, if all the weights in the neural network get big enough, then if we double all the weights, the neural network's going to operate exactly the same, right? So this means that in the weight space, say we go out here and we have a value of a weight space out here. Here's weight 1, here's weight 2. And suppose we have a value of the weights here. And suppose that at this point the neural network is saturated. Then the output of the neural network is going to have a value of an output here. Well, what happens if we triple all the weights? Well, it's still going to be saturated and it'll still roughly have the same output here, won't it? Okay? And if we multiply all the weights by 50, it'll still have the same output. Well, if it still has the same output at all of these points, then if we look at the error surface, which is a function of the weights, the error at this point will be exactly the same as the error at this point, etc., once the neural network is saturated. So therefore, we get to a point on array being one which passes through the origin, wherein if we keep going out on that array, we have the same input-output neural network relationships. If we look at locus of points along rays, like this, we get cones. Now, this does not happen for in here. It does not happen within the circle close to the origin. The neurons actually have to be big enough to saturate. So the error surfaces out here are eventually going to become conical and actually exist on ridges which are radiate from the origin. And indeed, we see that. What is more interesting is that these radial sort of surfaces are kind of like plateaus. And here's a way to visualize them, if we could go in here. You can see the origin. This is a two-dimensional error surface and a two-dimensional weight space. And we see in here, as we might expect, that the weights right in here are fine, but now we've gotten saturated and we see this conical behavior in 2 dimensions. These cones will also exist in 50 dimensions, right? You have 50-dimensional cones going out, wherein the errors remain exactly the same. So we have this sort of behavior here. What is very interesting is that in this behavior, we have a plateaus, which makes steepest descent very difficult. Because if we look at the gradient here, it's almost we're not standing on a hill anymore. We're standing in a meadow with a very gentle slope downhill. So, boy, we got to be real sensitive to which way we take the step. So this is what happens. Now, if you remember that the error space is a function of your training data. You change your training data, you change your weight space, right? If we have the same exact problem, except with more data, it turns out that these ridges become closer together. So our meadows, you notice this little meadow here, this little flat spot here and here, these meadows begin to tighten up as we increase the amount of training data, which makes sense. You should be able to train and to find the minimum error. You should be able to find the minimum error more easily if you have more data, which is consistent. Now, in this case, what's the minimum that we want to find? What weights do we want to use? We want to use the weights down here, right? Because these weights give us the minimum error. So if we generate a steepest descent sort of operation, we start at a point with which are the weights, and we begin to go downhill. We fall off a hill, go down here, fall off, and eventually, hopefully, get down here. But this is another interesting aspect, too, is that if you are at a minimal space, many times there's lots of slop in your weights, which will not affect your error very much. And this is very nice for the training of a neural network. You don't have a specific region of weights or you don't have specific values of weights that you need to find. As long as you can get within this region, you're going to be doing okay, at least in this problem. Now, you'll notice here in this case where you have more training data, this training data clearly was not in such a manner as to affect the plateaus here, but it did increase the ridges here, and certainly once we begin to fall downhill here to the minimum, it works much better in order to get us to the minimum. But again, two things that we notice about this. Number one is that the ridges are, that these error surfaces do have these plateaus on them, number one, and that number two, because of the saturation of the neuron, that these error surfaces have a conical sort of structure to them, which indeed you might expect. Saturation of a neuron is bad. There is a concept of neural network training in general referred to as plasticity. Plasticity is the ability to train a trained neural network more. Okay? You want to train a neural network that has been trained more. You train it, for example, for bushes versus trees, and here you have this neural network. All of a sudden you're using it for sorting bushes and trees, and all of a sudden there's some more information comes in that you want to update, you want to train this neural network more to distinguish between bushes and trees. If the neural network is plastic, if it has a high degree of plasticity, you should be able to introduce this new training data and to further train the neural network. That is the general concept of plasticity. You will notice that if a neuron is saturated, it becomes very unplastic, doesn't it? Because it takes a lot of changes in order to get this to the region where it can actually change things a little bit, right? So therefore, in many cases, if you train a neural network and you get it saturated, that might be fine for your training, but it takes away from the plasticity. There are ways where you can take a saturated neuron and basically chunk it back here by doing adding a little bit of noise to the weights actually, in order to get it plastic again. So that's just a general comment and to try to introduce the concept of what a plastic neural network is. Also, these error surfaces are such that the ridges are dictated by the slope of the sigmoid. You'll notice that the sigmoid here, as we have it drawn, doesn't have a parameter associated with it. There's no parameter. This is a 1 over 1 plus, no, that's not working. 1 over 1 plus e to the minus x. There's no parameter associated with it, right? However, if we put a magnification parameter in here, say an e over m, we could actually soften this slope. It always is going to go through the origin here. But if this is m is equal to 1, which corresponds to the first sigmoid, if we did m is equal to 2, that would essentially stretch out or magnify, if you will, the sigmoid to make it a smoother sort of function. Why might we want to do this? We might want to do this because the plateaus here are totally dictated by the slope of that sigmoid. And if we soften the slopes of the sigmoid instead of this relationship with the plateaus, we get this relationship. This is the error surface for that same problem using smoother sigmoids as plateaus. I'm sorry, smoother sigmoids. And you can notice that the plateaus are smoothed out, and we have less of these shelves that we have to worry about.
Do you have to take smaller step sizes if you do that?
Do you have to take smaller step sizes if you do that? Yes, maybe. It's really hard to say. Why did you say that?
Well,
Why would you think?
If you start to smooth it out, the gradient in a local area, you'd have to be more sensitive to the gradient.
Well, here is actually an interesting point. Maybe it's a good point to introduce it because of the question. If you're doing a gradient descent and you're on one of these plateaus, what sort of step size do you want to take? That is, that you're a place and you see, okay, it's going downhill, but man, it's not going down here very fast. Seems like you want to take a big step, right? Whereas if you're standing on a really steep edge and you want to go downhill, you might just want to take a little baby step, right? So this would be an example, in fact we'll get to it, is something called the delta bar delta rule, which actually adapts the step size in accordance to the gradient that you're on. If you're on a flat spot, you take a big step. If you're on a steep spot, you take a little step. Okay. By the way, what does a big step and a little step remind you of? Fuzzy, right? And couldn't we, in fact, we do have fuzzy backprop, which we'll talk about in a little bit, maybe not today, but fuzzy backprop basically says if you're on a flat slope, you take a big step. If you're on a little slope, you take a little, if you're on a steep step, you take a little. Do you know what I'm trying to say? Okay, if you're on a shallow slope, you take a big step. If you're on a steep slope, you take a tiny step. Could you make this into a fuzzy linguistic rules using fuzzy membership functions? Yeah, if you had a little experience in doing so. And so we actually have fuzzy control of backprop. Probably the most commonly used technique for adjusting the error, however, is the delta bar delta rule, which actually is very similar to backprop. So we'll talk about that. Let's talk more about the error surfaces. And by the way, the error surfaces and the examples that I'm giving you are very data dependent. These are just kind of rules of thumb. And if you come up with a problem and you're playing around with it, you say, man, it doesn't look like the error surface should be that. It probably isn't. The data's probably screwed it up some way. Okay, so these are commonly occurring error types of surfaces, but they are not always of this type. One of the techniques which was popular in order to avoid saturation was to, for cases where the neural network was used for a binary classification of +1 and a -1, to instead of having the targets on the output be a +1 or a -1, have the targets be a 0.9 and a -0.9 using a hyperbolic tangent. In other words, if we were training jockeys and basketball players, we would put in a jockey and the target would be a 1, would put in a basketball player be a -1, jockey 1, basketball player -1. Well, this tends to saturate the neural network because you are asking the most drastic adaptation that can occur. So instead, let's do this. Let's put in the basketball player and ask for a -0.9. Put in a jockey, ask for a +0.9. Put in a jockey, ask for a +0.9. Basketball player, -0.9. Get the idea? In other words, soften our requirement in our training data instead of from 1 to -1 in order to allow ourselves to stay away from getting the saturations. Oh, this works nicely, except that typically doing so in classification problems introduces local bad minima into the error surface, which sometimes you can live with and sometimes you can't. Can we zoom in on this, please? Here is exactly the same training surface that we looked at before, except now, excuse me, this is page 116, by the way, except now that the output has been put at -0.9 and +0.9. And what is interesting, if you look very, very closely, is that between the plateaus and the ridges, there are little gullies which have formed. You see these? You see those? Well, it turns out if you get trapped in one of those, and here's another reason for using momentum. If you get trapped in one of those and you hit, boom, one of those right in the middle and you go steepest descent, you'll always be staying in that gully. You'll never get out of it. Notice if you had momentum, you might have the momentum to cross over a gully into the next lower minimum, right? If you had some momentum going for you. But if you didn't have some momentum, you can indeed get trapped in these false minima. Again, where we want to be is down in this region. Where we might end up is, let's see, we might end up in this gully, which gives us a small error, which, might be acceptable for engineering practices, but if we could get down here, that would be better. By the way, what sort of error do you want to do? What's acceptable? What's an acceptably small error if you have good generalization? It's very engineering application oriented. And in fact, it's a good question to ask before you even start training the neural network. You look at the neural network, say, I'm going to apply the neural network for this problem. I'm going to apply this problem to this methodology, whatever. And in order for me to be successful, the neural network has to do A, B, and C. And that's your criteria. And it might not be, and this is one of the nice things about a neural network, it might not be totally required for you to find a global minimum. Maybe you can find a local minimum that will meet your engineering objectives. Indeed, if it does, hey, that's okay. It's going to work. So anyway, this is one of the problems of replacing it by a -9 and a minus 0.9 and a plus 0.9 instead of a -1,1. You do get these false minima. And by the way, the false minima are data imposed. Here's an example. This is on page 117. This is going back to the plus-1 sort of realization again. And here's data which isn't linearly separable, and you can see these false minima which occur. And you'll notice again that the false minima occur and the neural network is saturated at this point, so proportionally increasing the weights is going to keep the error of the neural network exactly at the same place. So you will typically have local minima that one needs to get out of and one needs to avoid. One of the ways to do that is with sufficient momentum to carry you over the local minima. That's one of the reasons to use it. There are other ways to get around it also. Okay, any questions on that? It's a basic heuristic overview of the surfaces and the error surfaces and what happens. There's really very little math associated with what we've done here. Okay. I want to talk about some faster variations of backpropagation. One of the things that I mentioned is that backpropagation takes a very, very long time to converge typically, and there are some faster ways of doing it other than direct steepest descent, although many of the techniques are actually variations on steepest descent. Probably the most commonly used is Fallman's algorithm called quick prop, which totally abandons the steepest descent sort of algorithm and uses Newton's method for minimizing f of x. You have to realize that steepest descent is not the only technique which can be used to find the global minima. There is a whole list of them. In fact, I know that they're in the they're actually outlined in the back of the text. Unless they moved it. I guess they moved it. D, step inside. Yeah, I don't see it. Anyway, Russ Reed, the co-author of the book, placed these in the within a chapter. And you have to realize, again, people get their entire PhDs solving these sorts of problems, finding the minimum of an objective function. Not only doing that, but figuring out a good way to form the objective function so that it can be solved relatively easy. Well, there's a number of ways to do this. One is Newton's method for minimizing a function f of x. The concept that Newton used was that the delta x was equal to minus f prime divided by f double prime. Let me explain to you what we mean by that. Newton's method, as we mentioned here, assumes that the error that you're looking at is basically parabolic, and an opening parabolic sort of relationship. So let's put it within the context of what we're talking about. This would be the error function, and of course what we would like to do is we would like to find this result at this point. One way to do this is to not look at the error surface, but actually look at the rate of change of the error under the assumption that this is quadratic. Under the assumption that this is quadratic, this is going to be an error surface which, let's say, has a negative slope, right? It's going to be constant. First derivative of quadratic is a line. And what point in this line are we trying to find? We're trying to find the value where the slope is equal to a minimum, correct? So indeed, if we have this, let's assume that we are at a point for this quadratic surface, and we have actually looked at the rate of change. By the way, this is the rate of change of E with respect to the weight. And we looked at the rate of change of E with respect to the weight at time -1, and our new step has taken us to this point, which is the rate of change of E with respect to T dW. So this was our old point, and this is our new point. We're coming down. Now, these have corresponding values over here. I guess we can't do that exactly. But there are corresponding values over here. But actually what can be seen is in here a little bit better. Now, the idea is that we know, if we assume that we have a quadratic surface, that the closer we get to this zero crossing, the more we want to slow down, correct? If we're going too fast and we're close to it, then we would like to slow down. So how would we like to do that? The way we would like to do this is to make sure that our next step in some way is a percentage of the step that we have here. In fact, the new step size, if we let this be S of t, t minus 1, and S of t, the new step size is going to be S of t divided by S of t minus 1 minus S of t. In other words, we are going to take a percentage. We're going to take a percentage. The S of t minus 1 by S of t is what? This distance, correct? And what is the numerator? The numerator is the entire distance here. So we're going to be taking a percentage, if you will, of that distance for our next step. So our next step, which will be delta W of, let me use the same notation here, t, is going to be equal to delta W of t minus 1. So therefore, as we begin to get closer and closer to our result here, our percentages are going to slow down, and hopefully we will fit this very, very nicely. This is exactly Fallman's quick prop update. You will notice that in the neural network we have the rate of change of E with respect to W, don't we? I mean, this is the downhill sort of slope that we were being able to use. Now, Fallman's quick prop actually has two assumptions. One is that each of the error surfaces can be approximated by the parabola. By the way, this is a very common assumption in mathematics. They assume this in quantum mechanics, right, where they talk about the quadratic well. There's about 4 known solutions to Schrodinger's equation. One is with the quadratic well, and anytime you have a quadratic energy well, you apply anytime you have a convex sort of energy well, you apply a quadratic approximation and use that closed form solution to Schrodinger's equation that way. So that's one thing, which is the parabolic approximation. And the second one is that it is insensitive. Now notice that this is for a specific weight. This is for a specific weight. Now there's other weights elsewhere in the network. And if you change those other weights, it could be that this error surface is going to shift if you change another weight somewhere else in the neural network. Fallman is assuming that this shift is really insignificant. And under these two conditions, that we have a parabolic approximation and that it is insensitive to shifts corresponding to weight changes in other places of the neural network, quick prop works very well. And I think that we have found that in terms of actual implementation is one of the better ways to perform the training of a layered perceptron. So this is one of the fast techniques. Another fast technique is Jacob's delta bar delta rule. Now, Jacob's delta bar delta rule. Any questions on this one so far? Okay, Jacob's delta bar delta rule, which is on page 137 of your text, basically says the same thing that we alluded to before. If you're on a flat surface, you want to take big steps. If you're on a very steep surface, you want to take little tiny baby steps. So on page 137 of your text, we go to Jacob's delta bar delta algorithm. By the way, there's something I didn't mention in the quick prop. In the quick prop, there's no concept of a learning rate here, is there? There's no ADA. There's no free parameter to choose. So that's kind of nice. And each weight adapts differently. You have a weight in one part of the network, this coefficient for how you change your weight step is going to be different than in another part of the neural network. So each one of the individual weights is adapting in a different fashion, a different step size, if you will, depending on where it's at. This is actually kind of a second order, a discrete approximation to the second derivative, isn't it? Right? It's a discrete sort of approximation. This is also true in Jacob's delta bar delta rule. Jacob's delta bar delta rule, each of the weights has its own learning rate. And every learning rate varies over time. In other words, we had before that the weights, or the delta weights, were equal to minus eta as a function of E with respect to the weight. This was the update, and then this is without the momentum term. Well, if you'll notice that these weights here, there's really nothing that says that the step size cannot itself be a function of time. There's nothing to say that we can't adjust this weight or this step size as a function of time. And you can think of a number of ways to do it. We mentioned the slow versus the steep. Another thing, the closer you get to the origin, or to the, not the origin, but the closer you get to the solution, you might suggest that you want to take smaller step sizes, right? As you get closer to the solution, otherwise you're going to be overshooting it. When you're far from it, you don't mind taking larger step sizes. Here is Jacob's delta bar delta rule. The learning rate can be increased when the partial derivative of the error has the same sign over several steps. In other words, if your delta weight, if this is positive, you have a weight, and for one step you went this much, you increased it this much, then you increased it this much, then you increased it this much. You know, if you do it again, you'll probably get bigger, right? So next time, let's just not do a little one, let's do a big one. So if we get a lot of positive increments, well, let's make that step size bigger so that next time we don't have to do a whole bunch of little ones. On the other hand, if the step size, if here's your weight, and you go weight, increase, 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 decrease, decrease, increase, decrease, increase, 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 decrease, decrease, then you're really not sure what to do. But if it's always going in the same direction in a number of steps, increase, 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 probably you're going to keep on increasing, so let's make the step size larger. So that's one of the rules. Another one is the learning rate should be, I'm reading, by the way, off page 137 at the bottom. The learning rate should be decreased when the partial derivative changes sign several times in a row. So this is the converse. If indeed the weight is changing, so you increase, increase, decrease, increase, decrease, decrease, increase, decrease, decrease, decrease. I'm getting it all backwards. In other words, if you're jogging around, in a way that weight is kind of overshooting and oscillating back and forth, right? If it's oscillating back and forth, what do you want to do? You want to decrease the step size in some sort of fashion. So the point is if you have a lot of relationships which are very, very similar, then you want to increase that. If you're jogging around because of overshoot, you want to decrease your step size. And this comes to the delta bar delta rule, which is on page 138, which I'll write here. Now this is the change in the learning rate. The changing in the step size is a function of t. Not the change in the weight, but whether we're changing the step size. This is equal to kappa. If del bar t minus 1 del t is greater than 0, it's equal to minus phi times eta of t. If delta t minus 1 delta t is less than 0, and it's equal to 0 otherwise. Where the delta t's here, by the way, the delta t is equal to the rate of change of w with respect to t. Delta t is equal to 1 minus theta times del of t plus theta del of t minus 1. In other words, it's a convex combination of the two results. And the del is equal to the rate of change of E with respect to W. Okay, wait a minute. No, that should be, one of those should be overlined. Okay, good. Okay, let's take a look at this and kind of demystify it a bit. Kappa and phi are kind of step sizes for the step size, right? The step sizes for the step size. In other words, you have to define and decide how much you want to increase or decrease the step size. And so you do that by the choice of k and phi. Now, delta bar, and this is the reason it's called a delta bar delta, the delta bar is equal to 1 minus theta times the slope. This is the del E del W, the slope, plus theta times del bar. What this is an exponential moving average. It's the same, if you solve this, it's the same as taking the history of the delta functions and weighting the history in an exponentially damped fashion according to a time constant of theta. Is that okay? In other words, if I gave you the sum of k is equal to 1 minus theta x of k. Here we go. Let's do y of k. If I gave you this in a DSP class, you would have no problem solving it. Okay, it is a simple first-order recursion that has a solution. What is it? Something like theta to the k or something like that. Was that? Somebody said something. Is that right? Let's look at this. No. It's equal to a exponential sum. Gosh, do I have to solve this? Can anybody solve this? Come on, you guys. If we use, Yes, it should be. Yeah, good point. So if we use z transforms on this, we get what y times 1 minus theta, right, is equal to 1 minus theta. No, that can't be right. Oh, 1 minus, there it is, okay, 1 minus z inverse theta, right, is equal to 1 minus theta times x, correct? So I get that y is equal to 1 minus theta, 1 minus z inverse theta times x. And then if I inverse transform, well, let's see, we can do this a number of ways. Probably the easiest is expanding this into a geometric series. K is equal to 0 to infinity of z minus 1 to the theta raised to the kth power times x. Right, I've simply taken this and expanded it as a geometric series. Is that okay? So I get, if I inverse Z transform, what is Z inverse? I think I get Y of K is equal to 1 minus theta times the summation over K is equal to 0 to infinity of theta to the K, X to the N, let's see, I better make this an N minus K. So there I think we have our result. The point is, I don't know if this is exactly true, that Y sub n is a weighted average of past values of X. That's what Y is equal to. Y is equal to a weighted average of last values of X. So that if we had X coming up, here's X, these are our past values. What we would like to do is we'd like to multiply this by theta to the minus K, which is going to be something, or theta to the K, which theta is going to be less than 1, which will be something like this. So we will multiply this times this, add it to this times this, plus this times this, plus this times this. This is our theta to the K. And then this weighted average will be the value of Y here. So you'll notice it's a weighted average with an exponential weighting of previous values of the input. So that's what the delta bar is equal to. It's a weighted value, exponentially weighted value of previous values of delta. So it has a memory associated with it. Okay. You'll notice that if delta changes sign, then what has happened is that the reason it's called the delta bar delta rule here is that delta bar delta, if it's greater than 0, what does that mean? It means that you're going in the same direction as most of your history, right? So let's make the step size bigger. If, it should be delta bar. If delta bar delta is less than 0, it means you're doing something which is contrary to your history. So you want to slow down a little bit. Something new is happening in that case. So you want to slow down, and you would like to decrease your step size. And then if well, it's hard to be else. Kappa times a to t. Is that a typo in the book? 137. Yeah, you're right.
Well, no, it would still increase.
Yeah. You know, and actually I am not sure. Let me check on that and see if that's a typo or indeed that's... Yeah, it does say it's constant in the book, but I'm not sure. Let me check on that. I'll look at Jacob's original paper. So anyway, that is the concept of the Jacob's delta bar delta rule. And you can see here what we're doing is we're adaptively adjusting the step size. But you'll notice that Fallman's quick prop also does that same thing, doesn't it? By looking at the derivatives at various places, it adjusted the step size based on the derivative as opposed to any applied external parameters, because we still got to choose theta and kappa here, right? Okay, any questions at all? Okay, then we will see you on Thursday. And until then, happy trails.